In previous sections, we've focused our attention on matter. Now we're going to turn our attention to thermochemistry and look at the energy associated with the changes in matter. So energy is the capacity to do work or to produce heat. And just as we had a law of conservation of matter, we have a law of conservation of energy, which states that energy can be converted from one form to another, but can be neither created nor destroyed. This means that the total energy content of the universe is constant. When we look at energy, we can roughly divide energy into two categories. Potential energy, which is energy due to position, or in the case of a chemical reaction, energy due to composition, or kinetic energy, which is energy due to motion of the object. Kinetic energy depends on the mass of the object and its velocity, where kinetic energy is equal to 1/2 mass times velocity squared. As an example, let's imagine we have two balls on a track, where ball A is held higher in place than ball B. Therefore, A has a higher potential energy than ball B. If we let ball A go, its potential energy will become kinetic energy as it rolls down the hill and strikes ball B. At that point, ball A will transfer its kinetic energy to ball B, and ball B will begin to move until it comes to rest at some position on the track. Ball B should come to rest at a position lower than the original position that ball A held, because there's some loss of energy due to frictional heating of the track as ball A is rolling. Then there's some energy loss as ball A strikes ball B. So with energy, we have heat and work, where heat involves the transfer of energy between two objects due to a temperature difference. Now keep in mind that heat and temperature are not the same thing. Temperature is a property reflecting the random motion of a collection of particles, and heat involves energy transfer. When we look at work, we're looking at a force acting over a distance. Work and heat are dependent on their conditions. However, energy is a state function, where a state function is a property that does not depend in any way on the system's past or future. It only depends on the present state of the system. Now let's really focus our attention on what's important to us, which is chemical energy. With chemical energy, we're looking at a difference between starting compounds and products. There is an energy associated with a chemical bond. When we break chemical bonds in a chemical reaction and then reform chemical bonds in our products, we can look at the difference in energy between the products and the starting materials. We want to define what we're looking at. The system is the part of the universe on which we will focus our attention. It is the chemical reaction of interest. The surroundings include everything else that is not the reaction that we're focusing our attention on. The surroundings are everything else in the universe. The reason that we want to focus our attention and define the system and the surroundings is that we want to be able to say which direction energy is flowing. In an endothermic reaction, heat flows into the system to drive the reaction. The system absorbs energy from the surroundings in an endothermic reaction. In an exothermic reaction, energy flows out of the system. In an exothermic reaction, the surroundings gain energy. The energy gained by the surroundings must be equal to the energy lost by the system. So let's think about freezing of water and determine whether this is endothermic or exothermic. The freezing of water is exothermic because energy must be removed in order to slow the molecules down and form a solid from a liquid. Now we can go through and classify each of the following processes as exothermic or endothermic and give an explanation. In each case, we're defining the system and it is underlined. So if the system is your hand, which gets cold when you touch ice, we're looking at an exothermic process because heat energy leaves your hand and moves to the ice. When ice is the system and it gets warmer upon touching it, we're looking at an endothermic process where heat energy is flowing into the ice from your hand. When water boils in a kettle being heated on the stove, it's an endothermic process. Heat energy flows into the water and boils it. Water vapor condensing on a cold pipe is exothermic. Heat energy leaves to condense the water from a gas to a liquid. And when ice cream melts, we have an endothermic process. Heat energy flows into the ice cream to melt it. For each of the following, we'll define the system, its surroundings, and give the direction of energy transfer. When methane is burned in a Bunsen burner in the laboratory, we're looking at a combustion reaction between the system, methane and oxygen, which produce carbon dioxide and water. The surroundings are everything else around it. And here the energy transfers from the system to the surroundings in an exothermic fashion. When water droplets sitting on your skin after swimming evaporate, our system is the water droplets, the surroundings are everything else, and the direction of energy transfer is from your body, which is the surroundings, to the system, the water droplets, in an endothermic fashion. Now let's think about hydrogen gas and oxygen gas reacting violently to form water. What's lower in energy? A mixture of hydrogen and oxygen gases or water? Water is lower in energy. The fact that the reaction is giving off energy in a violent fashion tells us that water is lower in energy than the components hydrogen gas or oxygen gas. In an exothermic reaction where energy is released, the product is lower in energy than the starting materials. In an endothermic reaction where energy is absorbed, the product is higher in energy than the starting components. So thermodynamics is the study of energy and its interconversions. Therefore, the law of conservation of energy is oftentimes referred to as the first law of thermodynamics, which again states that energy cannot be created nor destroyed, only converted from one form to another, and the energy of the universe is constant. So let's talk about the internal energy of our system, E, which is the sum of kinetic and potential energies of all of the particles in our system. To change internal energy of a system, we have to have some heat or work done, where change in energy is equal to Q plus W, where Q represents heat and W represents work. Our thermodynamic quantities will consist of two parts. We will have a number part, which gives the magnitude of the change, and then a sign which indicates the direction of the flow of heat. Our sign reflects the system's point of view. So in an endothermic process where heat is flowing into our system, Q is positive. Energy flows from the surroundings into the system. Our change in energy is greater than 0. In an exothermic process, Q is negative and energy flows out of our system into our surroundings. Our change in energy will be less than 0 in an exothermic fashion. With work, sign also reflects the system's point of view. If the system does work on our surroundings, then work is negative. When the surroundings do work on the system, then work is positive. So if we look at a piston moving in a cylinder, work is equal to force times distance. The distance is the change in height of the piston in our cylinder, so work is equal to force times change in height. Since pressure is equal to force over a unit area, we can rearrange that so that force is equal to pressure times area and get that work is equal to pressure times area times change in height. Change in height times the surface area of the piston is equal to the change in volume in the cylinder. So work is equal to pressure times change in volume. For an expanding gas, our change in volume is a positive quantity because the volume is increasing. Thus, our change in volume and work must have opposite signs because a gas expanding and increasing volume is work being done on the surroundings. So work is equal to negative pressure times change in volume. In some cases, we'll have to convert between liter atmospheres and joules. When we do, we have the equivalency statement that 1 liter atmosphere is equal to 101.3 joules. So now let's determine which of the following performs more work. A gas expanding against a pressure of 2 atmospheres from 1 liter to 4 liters, or a gas expanding against a pressure of 3 atmospheres from 1 liter to 3 liters. In both cases, we will use that work is equal to negative pressure times change in volume. In one case, we have a change in volume of 3 liters. In the other case, we have a change in volume of 2 liters. So if we set our work functions up for A and B, we should see that they perform the same amount of work. In case A, we have 2 atmospheres times a change in volume of 3 liters, which gives us work of -6 liter atmospheres. And in case B, we have 3 atmospheres with a change in volume of 2 liters. 2 times 3 is also 6. So in both cases, we get -6 liter atmospheres.